We move through a world that's governed by these invisible rules, these laws of physics. And most of the time, we don't even notice them. But in that split second, that incredibly violent moment of a car crash, those rules become crystal clear. So today, let's dive into the wreckage and use the physics of a collision to really understand the fundamental laws that shape our entire world.
So what is really going on in that fraction of a second when metal meets metal? It might look like pure chaos, but it's not. It's physics. For this explainer, we're going to be like forensic investigators, using the laws of motion to break down a crash, piece by piece, moment by moment.
Okay, so before we can even analyze the crash itself, we need to speak the right language, the language of motion. So the very first step in our investigation is to figure out how physicists describe something before the moment of impact.
First up, a really important distinction. Imagine this. Your car drives 10 kilometers down a perfectly straight road, then it turns around and drives back 3 kilometers. Now, the total distance you've traveled is pretty simple, right? It's 13 kilometers. But your displacement, that's your change in position from where you started, is only 7 kilometers. See the difference? Distance is the whole journey. Displacement is just how far you are from your starting point.
This is just as critical. Your car's speedometer, it tells you your speed, let's say 100 kilometers per hour. But for a physicist, that's only half the story. Are you going 100 kilometers an hour north or south? Velocity is what includes that direction. And in a collision, well, the difference between heading east and heading west is everything. Direction really, really matters. So what this all boils down to is that to properly investigate our crash, we need more than just a number. We need a direction too. Quantities that are just a number, like speed, we call those scalars. But the ones that have both a number and a direction, like velocity, we call those vectors. And believe me, in a collision, vectors are the whole story. All right, so we know how to describe the cars before the crash. But why is their motion about to change so incredibly violently? The answer to that question comes down to one single, powerful concept: force. It's kind of wild to think about how long it took us to figure this out. For almost 2,000 years, everybody just went with what Aristotle said. Heavier things fall faster. It seemed like common sense. It took Galileo, literally dropping stuff and rolling balls down ramps, to show that wasn't right. And then along came Isaac Newton, who put all the pieces together into 3 beautiful laws that are now the bedrock of our whole investigation. Newton's first law is all about inertia. Basically, it's an object's resistance to changing what it's already doing. If your car is zipping along at 100 kilometers an hour, guess what? So are you. And if that car suddenly smacks into a wall and stops, your body's inertia wants to keep right on going at 100 kilometers an hour. That net force from your seatbelt is what stops you. Without it, the windshield provides that force instead. His second law gives us that legendary equation, F equals ma. And this is the heart of it all. It tells us that force, mass, and acceleration are all tied together. If you want to accelerate a car, you need a force from the engine, right? A bigger force gives you more acceleration, but a heavier car, more mass, is going to accelerate less for that very same force. It all has to balance out. Now, this law clears up a huge misconception about crashes. Forces always come in pairs. So when car A hits car B, the force that car B pushes back on car A with is exactly equal and opposite. It's not like the bigger car wins by hitting harder. No way. The forces they exert on each other are always a perfect match. Okay, we've set the stage with the laws of motion. Now, let's zoom in on that critical moment of impact. During a collision, there are 2 key physical things that get exchanged between the objects. I like to think of them as the currencies of the crash: momentum and energy. Momentum, which we write with a P, is pretty straightforward. It's just an object's mass times its velocity. You can think of it as inertia in motion, or basically how hard it is to stop something. And get this, a huge truck moving slowly can have the exact same momentum as a tiny car moving super fast. And since velocity is a vector, momentum is too, which means its direction is absolutely crucial. Okay, let's put this to a practical test. We've all heard that modern cars are designed to crumple in a crash. But that seems kind of backwards, right? Wouldn't you want your car to be as rigid and strong as possible? Well, physics has a life-saving answer to that. And the answer is a concept called impulse. Now, don't get thrown by the formula. It's actually really simple. It just says that the force multiplied by the time of the impact, that's F times delta t, where delta just means change in, equals the change in momentum. This simple little equation is literally the key to saving lives. And here it is. This is the secret. In any crash, your total change in momentum is fixed. You have to go from 60 miles an hour to 0. But that formula gives us two ways to get there: a massive force over a really short time, or a much smaller force over a longer time. That is exactly what a crumple zone does. By deforming, it stretches out the time of the collision, which drastically reduces that dangerous peak force that gets to the people inside. It's genius. So what about the other currency, energy? Well, in a real-world crash, which we call an inelastic collision, the total momentum before and after is conserved. It stays the same. But kinetic energy, the energy of motion, is not conserved. So where does that lost energy go? It doesn't just disappear. It gets transformed into the horrible sound of the crash, the heat you'd feel on the twisted metal, and all the energy it takes to bend and break the car's frames. Okay, we have all the tools we need. Let's put everything together to analyze the aftermath of a crash and see just how powerful these laws of physics really are. This is where it all comes together. So picture a heavy car heading east and a lighter but faster car heading west. They hit head-on and stick together. Which way does the wreckage go? Well, the law of conservation of momentum lets us predict the outcome perfectly. We just add up the momentum going east and subtract the momentum going west. And in this case, the heavier car's momentum wins out, and the whole tangled mess gets thrown east at 5.71 meters per second. That's the power of physics. It doesn't just explain the crash, it lets us predict the aftermath. So these laws from Newton, the ideas of force and momentum, they perfectly describe our world, the world of car crashes, baseballs, and planets orbiting the sun. This is the physics of our everyday lives. But what happens when you start getting close to the speed of light, or when you shrink down to the size of a single atom? Well, at those extremes, the rules change, and you enter the incredible realms of relativity and quantum mechanics. But that's a story for another explainer.